Welcome to this GlobalSpec Quality Test and Measurement online event. Suppliers and OEMs can use dimensional engineering in a virtual simulation environment to view how assemblies fit together, and then adjust tolerances or properties to achieve cost and quality goals. Now, before introducing our speaker, we'd like to invite you to submit questions at any point during this presentation by using the Submit Question button at the base of this video console. Also, some of the presentations you will see today include detailed information, so we would encourage you to click the Download PPT button so that you can follow along with your own copy of the PowerPoint slides. Don Jasurda brings more than 30 years of engineering process improvement experience to his role as Vice President of Business Development at Dimensional Control Systems Incorporated. Don, welcome to today's event.
Hi, I'm Don Jasurda. I'm going to talk today about dimensional engineering as a means of supporting the quality assurance process in a manufacturing organization. To start with, I'd like to talk about problems and what kind of problems it is we're trying to address by this approach. The first thing we talk about is process inconsistency. Where are there discrepancies in how things are being made? Second thing we like to talk about is nonconformance. Where are specifications not being met? Where are products not adhering to their design criteria or objectives? And thirdly, the area we talk about is traceability, and that is where are there gaps in compliancy requirements, say for FDA or FAA or other types of traceability in those sorts of, and not only in regulatory agencies, but just traceability that have to do with keeping track of things from the standpoint of product record. How do these problems typically show up? Well, these first two are typically things that show up during the manufacturing process. Problems like rework, scrap, or changes to tooling, which are typically pretty expensive problems to deal with. Those are an issue in and of themselves, but this last one gets very, very expensive when it shows up because it typically comes in the form of warranty or liability claims once the product has been shipped to the customer. So the whole idea is try to address these and ultimately eliminate these. So how are we going to do that? Well, the process of dimensional engineering is a process that starts very early in the product development cycle. Even before any designs are created or defined, there are directives that are defined. Things like what are the materials that are going to be used in this product? What sort of manufacturing processes might be used because of those materials? Is this going to be an outsourced component or subassembly versus an internally manufactured part or subassembly? And then what are the build objectives and strategies around supporting those manufacturing requirements, and right on through supporting things like GD&T, using tolerance analysis, having measurement plans to convey design intent to the plant floor, and then using data collection and reporting to perform root cause analysis and problem solve during the manufacturing phase. If we look at why we do this, it really is quite simple. If you look at dimensional engineering from the standpoint of the overall engineering process, typical cost accounting says that about 5% of the cost of a product is attributable to the design process, and then 50% to materials, 15% to labor, and about 30% to plant burden. But if you look at where the real cost of the commitment is made to the cost of the product, it's early in the process. During the design phase, 70% or nearly 3/4 of the cost of the product has been now defined, and that takes into account not only things like materials, but takes into account what are the manufacturing processes, what are the facilities that are going to be required, what are the all of the ancillary and supporting requirements going to be for this product, are all pretty much set based on what the design criteria are. And so that's why when we take a look at this process, we realize that the ability to deal with these problems and to mitigate these problems at this stage is very, very good, and the cost is very, very low. Oftentimes you'll hear people talk about robust design. Robust design is a concept that is very popular these days, but is really no different than design for Six Sigma, design for manufacturability, or other similar types of initiatives that have been undertaken over the past 10 or 15 years. Very simply, it simply means that the design includes process characteristics relative to the manufacture of the product. So if we think about a robust dimensional engineering process, we talk about the step of variation analysis, or tolerance analysis as it sometimes is called. Variation analysis takes into account the build objectives, the process strategy to achieve those build objectives, and the GD&T, or geometric dimensioning and tolerancing specifications, which are really the language of defining what the allowable amount of variation is relative to manufacturing good quality parts. So those are the key elements of this. If we look at from a tools perspective, within the DCS product suite, we have 3 DCS for doing variation analysis that can be applied very early during the build objective stage, so that designs can be optimized in order to be able to accommodate or tolerate the most variation and still be able to realize or achieve the objectives for that product. If we talk about 3DCS from a more general standpoint, we then take into account things like locating strategy, how is the tooling going to be designed, and how is the tooling going to function relative to the parts and the product itself. And we take into account things that might have impacts like the effects of thermal change, or the effects of processes like welding or forces that are applied through clamping and things like that. Those can all be accounted for during the more traditional engineering stage of variation analysis. The next aspect then is to consider, through the use of the QTM tool set, the ability to generate a measurement plan which communicates the intent or the output, not just the intent, but the outcome of the simulations to the plant floor, so that measurements of actual parts can be performed in the same fashion they were during the simulation process, and then using that same information to do plant data analysis, and through the use of GDM Web be able to collect and problem solve plant floor problems relative to the build quality of the product, and then feed that back to engineering for correlation to what their design simulations said were going to happen, and for optimizing future designs, truly taken into account a design for manufacturability kind of initiative. So the closed loop approach to quality, from the standpoint of how DCS thinks about this, it starts very early in the engineering phase, and it centers around the prediction through the use of simulation of what the issues are going to be, where problems are going to occur, and how they can be addressed in order to try to alleviate or minimize problems before they occur in the plant. Once those optimized designs are are realized, those specifications are defined, then it becomes a need to communicate that information from the early stage engineering simulation to the plant in the form of a measurement plan or a quality plan. And so having the ability to transfer that information to the plant, and then using that same information to uncover problems that are occurring, because they ultimately will. No matter what you do from a simulation standpoint, there is still going to be some level of issue that is going to arise during the manufacturing process, just because of the numbers of variables that are involved. And so having the information available to quickly uncover and find those problems, and then use that information to be able to solve those issues through the use of quality data in an easy to understand, visible form, so that that can be then fed back to the engineers. So if we look at that first step in the predict stage, we talk about something called dimensional variation analysis, or variation analysis as it's more commonly known, and the use of in the DCS tool set a product called 3DCS. And so if we look at how 3DCS is applied throughout the entire product life cycle, here we see a generic concept of the product life cycle stages, starting at the concept stage and moving right on through to the in-service stage of the product life cycle. And we see two different types of digital variation analysis. We see something called rigid body, and we see something called compliant. And those are two different modes of being able to analyze things. First one, the rigid body is exactly that. It assumes that all parts, all objects are of a rigid nature. They're stiff, they're solid, they cannot move. The second and more comprehensive mode is compliant, and that takes into account the flexing that things will do due to impacts of manufacturing, such as the thermal effects induced by welding, or effects of pressure from clamping, or the effects of gravitational impact of putting one part on top of another part, for example. So all of those things can be accounted for through the application of compliant variation analysis. This is very, very closely related to finite element analysis or finite element modeling, which is commonly used in understanding the variables in the structural aspects of a product. So if you look at those two different types of variation structures, we then see these three kind of general domains that are existent in both of those worlds. Perceived quality is just what it says. It's the customer's perception of what is quality. So it's looking at how variation affects the visual or customer interfacing or interactive elements of the product. How does, for example, in an automobile, how does the hood to fender gap look, or the flushness of that gap? How do those things feel? Are they of a nature that a customer would perceive them as being of high quality? Same thing in maybe in an aircraft environment where a luggage bin is closing as you're putting your suitcase away and you close the bin. You look at it and say, okay, how does that look or feel relative to what you would perceive high quality to be? These kinds of things can be analyzed and optimized through the use of this capability. The second element, and broadest and most widely understood and used, is the idea of GD&T, or geometric dimensioning and tolerancing optimization. GD&T is literally the specifications that define what the quality conditions are supposed to be. This is the engineering language of quality that communicates from the design intent to the manufacturing realized product. And so through the course of doing variation analysis and doing the studies that are part of the analysis, the GD&T, the geometric dimensioning and tolerancing is optimized to its most ideal condition, and that is then what is used to communicate to all of the manufacturing organizations, whether they be internal or distributed through a supply base, of what the specifications are supposed to be in order to have a optimal quality product. And then the last item we see is as-built correlation, and this is the one that is probably the most still least applied and still greatest opportunity for growth and improvement in not only the quality of products, but in realizing and optimizing the cost of realizing quality products. That is actually collecting data, measurement data. So when physical products are made, they are measured. There has to be a way of determining whether these parts or subassemblies are meeting their intended specification. So they will be measured with a variety of metrology devices, or there will be tests made, all kinds of different measurements taken in order to be able to validate whether something met its specification or not. Well, all of this information, aside from determining whether something meets its specification, has value from its interrelationships of one set of data on a part to another set of data. And when we start looking at the roll-ups of all of this data, the collection and assemblage of this data, we start to realize that there is a lot of value that can be realized from looking at things, number one, from an assembled context based on the data, but not only from the assembled context, but it's correlating the functional actual build results to the original design intent in the form of what the GD&T spec said. So we look at the GD&T spec, we look at the actual measured data, and we correlate these two to see where there are still discrepancies and where we can close the gap, if you will, on optimizing a product design based on real product information. Where are some of the applications for dimensional variation analysis? They can be in structural or chassis, whether it's in automobiles, aircrafts. We have examples where structures such as power plants and buildings are being analyzed for their integrity because of the fact that when you're building these large complex subassemblies, like in a power plant, for example, we have customers that use this tool set to assemble nuclear power plants. They simply have to fit together correctly. There is no opportunity for trial and error during the assembly process. Imagine, if you will, a nuclear reactor that has 15 or 20 segmented subassemblies that have to fit together, each one of them weighing 15 or 20 tons, and it's going to be set in place with a large crane. There is not the ability to set that in place and move it and reset it and remove it and reset it, as you might realize with some small assembled components, getting them to fit together or getting some holes to line up simply doesn't, that opportunity does not exist. It has to go together correctly the first time because of the magnitude of what it is that's trying to be assembled. And so validation through this process has become critical in applications like these. And when we look at other applications, in the electromechanical world, where we're talking about very, very high volumes of parts that have to be assembled or manufactured at very, very fast production rates, there is, again, simply no room for error. And when we look at things like aircraft, where now we're seeing kind of these two worlds coming together, where you have a large monolithic structure, but you're also seeing build rates starting to move from 10 or 15 a month to 30, 40, 50, 60 a month, where we're now talking about building two complete commercial aircrafts in a day. Suddenly things that were processes where hand fitting and rework were commonplace and were an accepted means of manufacture in order to get something to fit together, it's no longer acceptable. I talked briefly when we were looking at the overall slide about the idea of perceived quality and the idea of visualizing variation early. Here is just one quick example of of a front-end module on an automobile, and if you look at the image on the left, you see that the gap condition between the hood and the fender is very, very small, as opposed to the gap condition on the right, which is much larger. And this, while these are two static images, within the 3DCS application, it's possible to look at the variation in a very dynamic sense and be able to understand what is acceptable, what isn't acceptable, and how are these things going to be perceived from a customer's perspective. Again, using the engineering analysis combined with high-end rendering, you see very good photorealistic images that are computer generated in a matter of seconds, with variation influences taken into account. In a more traditional sense, we see something like an in-depth variation or tolerance study. Here we're looking at what might be that light assembly we just looked at. In this case, it's a rear quarter of a vehicle. We're seeing the light assembly in the light gray that is then set into the rear fascia or rear end assembly in blue, and the fender and body side in red. And so we're seeing that how these fits can be accomplished, and we see this this picture in the upper right, where we see several little blue dots in space. Those little blue dots represent the tooling locators that are used in the plant to align all of these parts before the welding process takes place. So this variation study takes into account two body sides, a roof, a rear end, and a light assembly, and looks at the assembly process relative to the tooling represented by the little blue locators. And keep in mind that this study was done before any of this tooling was ever built or even completely designed. The only thing that was new for sure was where the locators were going to be in 3D space, and the tooling was all going to then be built to those locating schemes, those locating positions, so that all of the parts could be assembled to them, and these studies realized very early in the design process. Associativity to the CAD model. Here again, we look at the analysis being tied directly to the CAD information, and if it's available from the CAD model, the GD&T information, which may have been designed in the CAD structure. The GD&T, again, the geometric dimensioning and tolerancing, that represents the dimensional characteristics within the model. All of that is directly associative and communicable, so that the data can be read into the tolerance analysis, into the variation analysis process, and then once optimized, loaded back into the CAD model for permanent archival. Another capability that once these variation studies have been realized is now being able to tie this directly to things like cost constraints. So there's an optimization tool set within the 3DCS product family called Advanced Analyzer Optimizer, which allows for aligning of certain tolerance conditions to certain external conditions such as financial criteria, so that depending on the manufacturing processes that are being used, given tolerance amounts or tolerance conditions or tolerance ranges can have impact on what the cost is relative to the manufacturing processes that are being used. And so with this in mind, you can design to realize cost targets and also then come to the realization that maybe manufacturing processes have to change or can change if it becomes one of a more economical process in order to achieve the balance between optimized quality specifications and optimized cost. Moving on to the idea that we talked earlier about with compliant variation. Here we look at just a couple examples. We talk about things like the effects of force or gravity or thermal condition, and we look at the idea of being able to take into account, in this case, an example of clamping and welding. So how does that impact the variation in the product, and how does these process variables manifest themselves in terms of the variability that has to be dealt with or mitigated in the manufacturing process. And then finally, outputting this to a report. Once the analysis is completed, while this is typically done by a very small number of people in an engineering organization, those that are interested in this output can be a wide range of people, not only in engineering or in manufacturing, but in the quality organization, in purchasing and procurement, when talking about dealing with suppliers or material sources. So having the ability to have access to and be able to output the reports of the analysis and the details of this become very, very important. Next step, really, after the analysis is complete, is then to use those outputs and the results of that process to be able to communicate the measurement strategy to a metrology lab or to the plant floor, telling them where to measure the physical parts based on what was realized during the simulation process, so that there is close alignment between the manufacturing and design requirements. And then finally, closing the loop, if you will, taking the information that is collected and used to validate the quality process, in this case using the QTM web quality management system that's used to control or manage the build quality process, and loading that data back into the analysis model, the original analysis model that was used to simulate the process, using the actual data now as a root cause analysis tool to solve problems, the same problems that were encountered in the simulation, to use that same information to address problems found during the build process. So let's talk about where this is being applied today. General Motors. 2 years ago, Car of the Year, Chevy Volt. Truck of the Year, Chevy Silverado. Both of these vehicle lines made extensive use of this variation analysis process. And as you can see here, one of the managers from the body engineering area makes some specific statements as to the application of variation analysis and how it has benefited GM in these vehicles. And further utilization came in the form of application within the powertrain organization, and particularly as it related to using variation analysis to optimize the design of the Ecotec engine in the Ecotec program in a variety of elements of its design. GM's application of the DE circle, as they call it, starting very early with their definition during the early development stages, and right on through the concept, engineering, validation, and verification in manufacturing process through the concept through what they term the DE circle. Peterbilt, which applies this capability in the fit and finish of their over-the-road trucks. Again, similar but different application to what we looked at relative to the previous customer. Here we're talking about looking for best-in-class quality and customer perception. Chrysler, from the standpoint of a customer who was applying this variation analysis process throughout their entire development process, starting with perceived quality very early in the development stage, and then through the use of advanced manufacturing engineering, applying full statistical analysis on rigid bodies, and then on compliant assemblies, taking into account the effects of tooling and processes in the manufacturing aspect of the product, and finally then the collection of data from the plant and loading that back into their models in order to be able to use this to root cause and to optimize and correlate back to their design study. Jumping to the aircraft industry, Airbus, again, application of the tolerance management, as they call it in their world, during the early stages of definition of different assembly methodologies, different aircraft configurations, different manufacturing strategies, whether it's relative to composites or different composite assembly processes, different cutting technologies like water jet, maybe single barrel assembly techniques, as well as different methodologies for assembly strategy. And looking also at things like the variation or the difference between tail and wing mounted engines, or different engine configurations that might make sense relative to the early phase design. Moving along then, as they move into the manufacturing phases, here we look at an example of applying the dimensional engineering process during the production launch, and in this case on the A350, where we're talking about the manufacture and measurement of a major component, say at a supplier, and then being able to use that data to be able to understand where variation is going to occur on parts, on parts that are going to get assembled at an Airbus facility, of parts that were transported from and integrated from various suppliers that could have been in multiple parts of the world. So as we look then at that and consider things like what are the rigging issues that they're going to encounter? What are in their world? There is a concept they refer to as untwist. That has to do with the force or something that gets applied, and what the impact of that is going to be to the assembly process, so that they can understand, okay, what kinds of adjustments need to be made, what kinds of of issues are they going to have to encounter and be able to address as part of the assembly process. They are able to understand and comprehend these problems ahead of time based on the measured data that is collected at their suppliers. So if we look at this from a complete process standpoint, again, we talk about the 8-step process, and really this idea of starting at the detail part level and then the relationship that occurs from detail part to subassembly to final product, and being able to close that loop is really the critical element of what supports the dimensional engineering process. With that, I would open it up for any questions or comments that there may be.
We do have some questions that have come in from the attendees, so let's get right to them. The first one asks, how would an approach like this be implemented?
Say again?
How would an approach like this be implemented?
So, from an implementation standpoint, it can be implemented really we always consider there to be kind of 3 major areas of impact of where dimensional engineering applies itself. The first is at the product development stage, and if you think back to that third or fourth slide we looked at of the impact of cost, we realize that this is probably the most important place for it to be realized, but oftentimes may not be considered because during the product development stage, people are not often as concerned about assembly and assembly characteristics, and so we oftentimes see dimensional engineering getting first applied during production engineering. At production engineering, there is still the ability to influence tooling decisions, locating strategies, things like that. But at that point, the designs are pretty much frozen, and it becomes much more difficult to influence design changes that could have a positive effect. But we see this applied at the production engineering stage as well. And then thirdly, at the plant floor stage, we have the ability to collect data and be able to make adjustments, very much like the functional build process that's used within some automotive companies that uses results based on what the actual measurements are. But typically, this approach has the least influence over addressing variation at the in the design of the product, and really now separates the manufacturing and the design functions from one another, as opposed to the idea of looking at variation early and bringing those 2 worlds much more closely together, so that when you start talking about the concept that is popular today, which is design anywhere, build anywhere, when you talk about design anywhere, you really have to take into account this notion of robust design, so that the manufacturing process and its constraints or limitations are really becoming a critical element of the product design itself.
Thank you. Another question, do I have to have a specific software in place in order to implement this system?
So this approach is kind of about it is about software to some extent, but it is also about people, and it's about approach. And so if you think about the concept of dimensional engineering, there are many aspects of it that touch on standard design and standard design process, good design process, also on production process. So if you think about companies that are applying production systems, I don't know of any significant OEMs in the automotive, aerospace, industrial machinery space that aren't applying some sort of production system, whether it's a production system like TPS that has been embraced and acknowledged as a fundamental approach to manufacturing product, or some derivative approach that a manufacturer is applying. Like, I recently was introduced to world-class manufacturing at Chrysler. Again, a very well thought out and very consistently applied production system throughout the world. This I think, applying systematic approach to dimensional engineering and dimensional analysis is really the critical element. Yes, software tools are an important element of it, but it's taking a systems approach that is going to be most critical.
Thank you. Another question. I work for a small business and we don't have a lot of procedures, process, or locations. Is this something my company can take advantage of?
So if you think about this from the standpoint of the four elements of the closed loop: predict, plan, find, resolve. As a small company, you are probably either only doing design work for somebody, in which case the simulation or predict element could become very relevant to you as a design source to your customer. Or if you're a manufacturing supplier, that isn't so important, but the ability to understand, to be able to find problems when they are occurring on your plant floor and be able to resolve them quickly, that now becomes very, very important to you. And your customer probably wants some feedback. Think about that traceability element that we talked about earlier. So being able to find and resolve issues and being able to provide that traceability link to your customer that validates your adherence to the design specification now protects you, if you will. And so as a small business, I would not anticipate anybody applying all of these elements, but all of these elements in and of themselves can be applied as standalone solutions to address individual problems within the overall scope of quality.
Okay, one last question.
Yeah.
Where in our development and manufacturing process should we be applying this kind of analysis?
So it kind of depends on what you're doing. If you're an original equipment manufacturer, say you're building an automobile or an aircraft, you're going to apply it throughout your product life cycle, starting at the concept stage right on through the production stage. If you're a tier 1 supplier, let's say you're delivering braking systems, you're delivering lighting systems, you're delivering interiors, instrument panels, those sorts of things. You're creating a product in and of itself that is going to be delivered to your OEM customer that's probably got some design requirements about perceived quality, and then it has interface points that are very, very closely managed. But within the context of your product, you are going to be manufacturing that product just as you're an OEM for your taillight, or you're an OEM for your braking module. And so you are you have the same issues as the auto manufacturer themselves does. And so being able to apply all of these capabilities throughout the process is relevant. Now, if you're a tooling supplier, or you're simply a manufacturing supplier where you're doing contract manufacturing, say making stampings to a customer specification. You're a build-to-print kind of shop where you're maybe stamping some parts and assembling them together in a welded subassembly. You're probably only going to have requirements for a certain element of the solution. But again, like my previous example, you're still going to be responsible for delivering to a set of quality specifications. Your product has got to meet quality goals, and your customer is probably going to want to have a level of traceability to be able to track that you are meeting those quality goals on a regular and continuing basis.
Don, that's all the time we have right now. We'd like to thank you for sharing your time and your expertise.
Thanks very much. I appreciate it. And my contact information is on the slide. If anybody wishes to contact me, drop me a note via email or give me a call. Thanks a lot.
Now, before moving on to explore the exhibit hall of this event, please take a moment to click the Take Survey button and let Don know how he did today. Your feedback helps us improve the quality of our GlobalSpec events, making them an even better investment of your time. In between sessions, head to the exhibit hall floor where you'll find manufacturer product reps, engineers, technical specialists, and other professionals waiting to answer your questions. Remember, you can see any of today's presentations during our on-demand period, but exhibitor representatives are only here on the day of the live event, so spend time with them while you can. Please experience our latest innovation, the Knowledge Exchange, offering product demonstrations and our hot topic audio briefs. The Knowledge Exchange is also home to our event price center. Share your thought leadership point of view by speaking at one of our events. You can find the speaker submittal form at our event help desk in the exhibit hall. We'd certainly like to thank you for choosing to spend your day with us, and we'll see you back here in the conference center a little later on.